All right, today we're going to dive into an idea that is genuinely, truly mind-bending. We're going to explore how the very definition of a mathematical proof got completely turned on its head, from being a static written document to a lively back-and-forth conversation. Let's get right into it.
So, I want you to start with this question. Just let it sit in your mind for a second. Forget everything you know about proofs being these dense textbooks full of equations. Instead, I want you to picture a really clever detective interrogating a super intelligent suspect. The detective's goal isn't to read some pre-written confession, right? No, it's to ask just the right questions to figure out with almost perfect certainty if that suspect is telling the truth. That, right there, is the core idea we're going to unpack.
But hey, before we can get to the cool interrogation stuff, we need to understand the old way of doing things. You see, for a long time, the model for a proof in computer science was way simpler. Think of it as a one-way street, a monologue.
And this old model is perfectly captured by the famous complexity class NP. Now don't let that name intimidate you. All it really means is that it's a class of problems where, if someone just hands you the answer, like, say, the correct path through a super complicated maze, you can check that it's the right answer pretty quickly. That answer they hand you, that's the certificate, or the proof.
So here's the crucial point. The whole process was totally static. You have a prover who we imagine has all the time and power in the world, and they just hand over the proof. Then you have the verifier who has limited power, and all they do is check it. That's it. No back and forth, no questions, just a simple handoff.
And then 1985 happened. Two different groups of researchers, totally independent of each other, had this revolutionary thought. What happens if we let them talk to each other? What if a proof isn't a document at all, but an interactive conversation? This one simple change, well, it opened up a whole new universe.
So this new model gives us two characters. On one side, we have the prover, who they nicknamed Merlin. Think of him as an all-powerful wizard, but he might be a little tricky. You can't necessarily trust him. On the other side is the verifier, Arthur. He's got limited realistic power, like a regular computer, but he's always honest. So the big question is, can a limited but honest Arthur figure out if an all-powerful but potentially dishonest Merlin is actually telling the truth? Now, to make this game actually work, you need two fundamental rules. First is completeness. This just means that if Merlin is telling the truth, he has to be able to convince Arthur. Simple enough. Second, and this is the really critical one, is soundness. This means if Merlin is lying, there should be almost zero chance he can fool Arthur. The probability of a liar winning has to be incredibly small. This is what makes the whole system trustworthy.
So you might be asking yourself, how does a limited little verifier like Arthur even stand a chance against an all-powerful wizard like Merlin? Well, Arthur gets a superpower of his own, randomness. And this turns out to be the secret weapon that makes this entire thing work.
See, by using randomness to decide what questions to ask, literally like flipping a coin to choose his next move, Arthur becomes completely unpredictable. Merlin might be all-powerful, but he's not a mind reader. He has no idea what random question is coming next, which makes it almost impossible for him to prepare a consistent web of lies. It's amazing how a little bit of randomness can totally level the playing field.
And this new model, this conversation, wasn't just a fun thought experiment. It literally defined entirely new classes of problems that we could solve. Classes with names like AM for Arthur-Merlin and IP for interactive polynomial time were born specifically to capture the power of this new conversational approach to proof.
And that right there was the big question that drove research for years. Okay, we know interaction is more powerful than the old static NP model, but how much more? Are we talking about a small step up, or was this a giant leap for computation? The answer, when it came, was a complete shock to the entire field. And here it is. In 1992, the legendary Adi Shamir proved that IP, the class of all problems you can solve with one of these interactive proofs, is exactly equal to PS space. This was an absolute bombshell in the world of complexity theory.
So what does IP equal P space actually mean in plain English? It means that this simple back-and-forth conversation is powerful enough to solve any problem that your computer can solve using a reasonable amount of memory. Think of it as pretty much any problem that doesn't require an impossibly huge amount of RAM to figure out. This is a massive class of problems, way bigger than anyone thought NP was. The power of a simple conversation turned out to be far greater than anyone had ever imagined.
But you know what? The story doesn't even end there. Researchers thought, okay, if one conversation is that powerful, what happens if we give Arthur another suspect to question? The model was about to get another massive upgrade.
And the inspiration for this next leap was just beautiful. It came straight out of a police detective show. A detective's job is so much easier if they can question two accomplices separately, right? Because if their stories don't match up perfectly, they're lying. So what if Arthur, our verifier, could do the exact same thing, but with two Merlin?
And this led to the creation of MIP, which stands for Multi-Prover Interactive Proofs. The setup is pretty much the same, but now Arthur can talk to two or even more provers. But here's the absolute crucial rule. Once the interrogation starts, those provers cannot talk to each other. They are in separate, soundproof rooms.
And just like you'd expect, giving Arthur the ability to cross-check answers between two isolated, all-powerful provers, well, it made the system exponentially more powerful. The jump this time was even more staggering than the last one.
So here's the result. MIP is equal to next speed time. And this class of problems it's unbelievably huge. It's the class of problems that could be solved by a hypothetical computer that can explore tons of possibilities all at once, even if it takes an exponentially long time. This is just an astronomically larger class than P-space, the memory-based class we just talked about. Simply by adding a second isolated prover, the power of the system just exploded.
So, where did this all lead? This whole journey of completely rethinking what a proof is, from a static book to a single conversation to a multi-party interrogation, it all culminated in one of the absolute crown jewels of theoretical computer science.
It's called the PCP theorem, which stands for probabilistically checkable proofs. And what this theorem did was take all the lessons we learned from these interactive proofs and apply them back to the original, static, written-down proofs, but with a completely shocking twist. The theorem is often stated just like this, which I know looks pretty cryptic, but what it implies is one of the most counterintuitive and profound ideas in all of mathematics.
So here is the absolutely incredible takeaway. The PCP theorem says that you can take any standard proof, and you can rewrite it in this special, really redundant format. But here's the magic. Once it's in this new format, you don't have to read the whole thing. You can just check a few bits completely at random, and if they're correct, you can be almost 100% certain the entire proof is correct. It's like verifying a million-page book is error-free by only reading 10 random letters. It sounds totally impossible, but the PCP theorem proves it works. And this isn't just a theory, it's the foundation for a ton of modern cryptography, like the zero-knowledge proofs that power things like blockchain.
And that's our journey for today. From the simple one-way proofs of NP to the conversational power of IP, the interrogations of MIP, and finally to the truly mind-bending spot checks of the PCP theorem. We've seen how our most basic assumptions about things like proof and verification can be completely overturned. And these ideas aren't just stuck in theory, they are actively securing our digital world as we speak, which really makes you wonder, what other fundamental ideas are just sitting there, waiting for someone to ask the right question?